if I asked you to expand this out, you'd be completely justified in simply just writing the 4 brackets out and then beginning to attempt to expand that. Now that is going to be prone to error and just inaccuracy. So, and that's only with a power of 4. So imagine if I gave you a power of 8, we're going to have all sorts of issues. So what we need to do really is use what we know about this to create something that makes it a lot easier and a lot more accurate to expand sets of brackets with higher powers than, say, just a 2 or a 3. So let's start to have a look at this a little bit. Imagine I started to expand these terms out. Now the first one is the obvious first of all of the brackets to be multiplied together. Don't forget, every term in each bracket has to be multiplied with every other term in a different bracket. So that's our easy, sort of obvious first one. 2 to the power of 4. 2 times 2 times 2 times 2. Now there's no other way of getting 4 2's, those 4 2's, to be multiplied to each other. That's it. That's all I've got. If I look at the next possible term, I guess, that would be 2 times 2 times by another 2, and then to make it different, instead of multiplying by the 2 on the end, I'm going to multiply by the 3. Now that gives me 2 cubed times by 3x. 2 times 2 times 2, 2 cubed, times by the 3x, 2 cubed times 3x. But hopefully you can see already that there are multiple ways that I could work that out. So I didn't have to pick the first 2, for instance. I could have picked the 3x from the first bracket and then the 2's from the remaining brackets, and that would give me the same value, 2 cubed times by 3x, but from a different arrangement of the terms that I'm expanding. Likewise, I could have taken the first 2 and the second 2, but taken the 3x from the third bracket and then the 2 from the fourth. So that gives me another mix. And then I could have taken the first 2 and the second 3x, the third 2 and the fourth 2. So I've actually got 4 different ways of organising these 3 2's and 1 3x. What about if I go for the next thing that I could do? So I could take a 2 and times it by a 2. But then if I times by another 2, I've already counted all of those. So I could times by a 3x and another 3x. So that gives me 2 times by 2 and 3x times by 3x, all multiplied together. Now, you could probably see already that there are loads of combinations that I could do that, sort of ordering, finding 2 2's and 2 3x's. In fact, there are 6 of them. So I could take the first and the last 2's and the middle 3x's. I could take the first and the third 2's and the other 3x's. Finding a systematic way through that problem obviously is quite difficult, but we're beginning to get somewhere with it. Next, okay, well I'm beginning to kind of run dry on this too, but I could do 2 times by the 3x, times by another 3x, times by a final 3x, and that gives me 2 times by 3x cubed. 1 2 times by 3x times by 3x times by 3x. Maybe already you're spotting that actually that would be kind of, it's the same combinations of one thing and 3 of the other, which would mean that there were 4 of them. If you're not sure about that, pause the video and just count through and make sure you're happy that there are 4 different ways of getting 1, 2 and 3x, 3 lots of 3x. And then the last term on the end, we could find by, well, in fact, we've only got one option left. I've run out of multiplying from this first 2 to anything, so I'm going to have to take the 3x on the end, the next 3x, the next 3x, and the final 3x. That's all I've got left to do. I've touched everything else loads of times, can't do anything more, and there's only that one way of doing it, so I've got 3x to the power of 4. Now maybe you're noticing some things already, and I hope that you are. If we look at the powers of 3x, we start in the first term with 3x to the 0, which is 1. And then we gain a 3x, and then in the next term we've got 3x all squared. And then in the last term we've got, penultimate term we've got 3x all cubed. And in the last term we've got 3x to the power of 4. In the opposite direction then, the 2's are going from having all of the powers, 2 to the 4. In the next one they have 2 to the 3. And the next one they have 2 to the 2. And then it's 2. And then it's none, 2 to the 0. So there's always 4 powers, if you like, if that's a way that makes sense to you. It certainly does to me, and hopefully you feel that. There's always a sum of 4 powers. There's a 1 there, 2 and 2, 1 and 3, 0, 4, etc, etc. And hopefully also you are spotting the number pattern here. So there's a 1 technically there, 4, 6, 4, and then another 1 down here to actually be part of Pascal's triangle. Here it is. Here's the line. 1, 4, 6, 4, 1. So I need some sort of formula that pulls all of these ideas together, because actually I could have had 7 terms, but that structure that we went through would still work. So let's see how far we can get generalising this. We worked out in the last one that the powers sort of moved between the terms in our expansion. So if we start this expansion, A has all of the power n, and B has none of them. And then in the next term, A would have 1 less power than it had before, because B has gained a power. And then in the next term, A would have 2 less powers than it had before, because B has got 2 of them. And we go on and on and on, and at some point the balance tips the other way, and then A is the one with the smaller power, because B's got most of them. And then A's got even less power, because B's got most of it. And then B's got all of it. We had that single term on the end. So you can see how this pattern is going to trot out at the end. What we haven't done is included our amounts of each of these terms. So the fact that we had 4 of those 2 cubed times 3x terms. But really hard to do that because we're trying to look for the nth row of Pascal's triangle. Well, that's literally no help to me at all. What I need is another way of calculating Pascal's triangle. So Pascal's triangle can be generated by the combinations formula, NCR, which is in your formula book as n factorial r factorial n minus r factorial. And this basically says the same thing as us asking, how many ways can I organise or pick, and then you insert the information. So this is the amount that you've got possible. So if we had a power of 4, we would say, from 4, how do I pick 3 2's? And then the formula would pull all of that out for you. Now your calculator also has the combinations button on it. Normally it's above your divide sign if you've got a standard calculator, and you need to go through a couple of options in your graphical calculator to find it. So it's something we'll look at in class just to make sure everyone can find that button on there. But this is the thing that generates our coefficients, so our number of ways we can organise. So this term would be n choose 0, or you could do n choose n, it's symmetrical, just as Pascal's triangle is. And then this one, nc1, nc2, so on and so forth, down to ncn over here. So let's go back to our example, and we're going to use the binomial expansion, as we now know. It's called the binomial expansion, that formula we just showed you, to expand this bracket out. I have a power of 4, so I'm going to start with 4, choose 0. Now we know that the first term, the 2 had all of the power, and the 3x had none of it. And then we do NC1. number of ways we can pick one, as it is 3x here, from 4 of them. So it won't be n, will it? Come on, Hannah, be 4. 2 cubed, because now 3x has one of the powers. And then 4, picking 2, 2 2s and 2 3x's. 4c 3, 2, 3x cubed, and then, oh, am I going to squeeze it in? 4c4, 3x, all of the power. From this then, we can just evaluate each of our terms. So 4 choose 0 is 1, 3 to the x is 1, it's all multiplied together, and then 2 to the power of 4 is 16. 4 choose 1, you can do it on your calculator, is 4. 2 cubed is 8, and then we've got 3x. So then 6, 4, and careful here, 3x squared is 9x squared. And then 4, 2, 27x cubed. And then 4 choose 4 is 1. 3x to the 4 is 81x to the 4. Sorting this out then, 16, and right, here's where my math starts to die. So 12 times 8, 96. Obviously you've got a calculator, so you're absolutely fine. You don't need to do what I'm doing and sort of try and multiply everything. I guess you get the idea, right? I just don't have a calculator with me. Sorry, whoops. Okay, let's do one more example just to make sure we're all on board with this. So first term, 7, because that's my highest power, and I'm going to pick no x's. 1 is going to have all of my power, and I have a minus x. So the minus must get included there. That has none of the power there. Let's just do up to the x squared term here. Let's not expand all the way, just go up to the x squared term. So there's my first term. Next one, 7 choose 1, 1 to the power of 6, minus x to the 1. 7 choose 2, 1 to the 5, minus x squared, and that's going to give me an x squared term. So I can show that it's going to continue, but otherwise I can stop. Okay, 7 choose 0 is 1, 1 to the 7 is 1, and anything to the power of 0 is also 1. 7 choose 1 is 7, 1 to the power of 6 is 1, and minus x to the 1 is just minus x. 7 choose 2, I believe, is 21. 1 to the 5 is 1, and then minus x times minus x is plus x squared. Okay, sorting all my numbers out. 1 times 1 times 1, 1. 7 times minus x, minus 7x. And then 21 times x squared plus 21x squared. And the comes out. And that's it.